let's get into the big topic of open source, something that we actually say at Red Hat.
We have a
This is so awesome.
are an open culture that believes
actually
in
a big
importance of
piece
What is that process that a developer, or let's say
As the Kubernetes ecosystem really boomed,
Hello, good morning, good evening, good afternoon, wherever you are in the world. I am Jonny Rickard. I am the co-host of the Ask an OpenShift Expert live stream. Sully will not be with us again this week. He had a medical thing that happened after Red Hat 1, but he will be back on our next stream next week. However, this week we're joined by Ben from Red Hat. He's are you a software engineer or product engineer? What's your job, Ben? I'm sorry. I was going to try and make something up, but I was like, it'll just get bad. So
they've titled me a senior principal software engineer.
Okay, awesome. And so we've been working now, or talking about this stream now for a little over a month. And I think when you came to us, it was more like, hey, people are using AI. There's things like Gemini. There's things like Cursor. People are using it, but nobody's really talking about like the infrastructure for all of this stuff, right? And so that's where kind of this stream idea came from. So yeah, do you want to talk a little bit about would you like to give a quick introduction about yourself and maybe talk about what you want to talk about today?
Sure. So yeah, I'm Ben Schmaus, and I am a senior principal software engineer here at Red Hat. I've been with Red Hat for 10 years, except for 4 months where I took a little sabbatical over at Dell. And I've been in a variety of different roles here at Red Hat, everything from technical account manager to a product manager to a field PM, and now my current role, which is a software engineer. And really, I just want to focus on the infrastructure underneath when people are trying to do, inferencing and training of large AI models that are going to need more than one node. Because that's key here. If you're trying to train something with a large data set and you're going to have multiple GPUs across a cluster of nodes, the network's going to come into play here. And we want to make sure that we're doing that the most efficient way we possibly can in order to make that AI inferencing and training more productive and happen quickly.
Awesome. Yeah, and I remember you as a product as a product manager, and so that's where I think I was getting hung up when I saw your title in the tab here. That's awesome. We're really looking forward to it. I'm an infrastructure person myself, but I'm also a big consumer of AI. So yeah, I think that this is going to be an awesome topic. Before we get started, though, I wanted to do a quick top of mind update. 421 OpenShift 421 went GA yesterday. So you can, if you're going greenfield, you can deploy a brand new cluster and you can do 421. It's there. However, if you're going to upgrade, the 421 channel is not unstable yet. However, fast is available. So let me go ahead and share my screen really quick. Maybe. So if we look, it's an OpenShift 420 cluster. So if I wanted to, I could change to the fast 421 channel and then do my update that way, or my upgrade that way. The reason why this is preferred is because you can go from fast 421 to stable 421 when the 421 channel releases. It usually takes 30 to 60 days. I mean, sometimes it's a little bit faster, but for the most part, it's about between that 30 to 60 day mark. And that's so they can find any bugs and get them released. But fast is a supported upgrade path to the stable channel. On top of that, there are a bunch of changes that are coming out, specifically. From what I remember yesterday, it was ACM looked like there were quite a few things coming out. External Secrets Operator and Cert Manager have quite a few significant upgrades, and then just more promotion of the Argo CD agent with the ACM. So basically centralized management. You can deploy an agent onto your spoke cluster. I'm using ACM language here, but it'd be your remote cluster would get the agent instead of having a full-blown deployed OpenShift GitOps Argo CD instance. So lots of cool stuff happening there. Yeah, other than that, like we've got a pretty full schedule coming up. We've got Chris Butler coming on to talk about Cocoa. We've got next week the Trusted Artifact Signer group is coming on to talk about the RHTAS project that's been happening at Red Hat for a while. If you've been following security and anything like that for the last year and a half. Like the trusted artifact signer has been a big part of that. And so they're going to come on and they're going to talk about how to use it, what it's about, and where it's going. So all of that, it's a lot. I see there's a question from Pixel. Apologize if I butcher your handle. I tried the developer sandbox, but it won't verify my phone number. Red Hat support claims that they cannot help as I do not have a subscription. What can I do? So have you, Pixel, if you want, you can shoot me an email. I'm Jonny at Red Hat, JONNY at redhat.com. But I would just shoot me your info, shoot me what's going on, and then I'll see if there's somebody I can put you in contact with to help work it out. But you should be able to go in and verify either through email or through a phone number, and get a developer account. That would, I guess, be my first question: is do you actually have a developer account on redhat.com? And if so, maybe check your phone number there or check your profile settings in there. But shoot me an email and let me know. All right, Ben, you ready?
Absolutely. Let's do it.
Do this. Let's do it.
Do you want to go ahead and get my screen shared for me?
Yep. Here we go.
There we go. So again, my name is Benjamin Schmaus. I have a few slides I want to go through. I don't want to bore us with a lot of slides because I wanted to show you guys more of a live setup demonstration of how we can actually do this on an OpenShift cluster. But I did want to kind of show you some of the reasons why RDMA, specifically GPU direct RDMA from NVIDIA, is important on OpenShift and how it's going to benefit you in your AI infrastructure. So with that said, let's go ahead and get going. So the big thing to understand is that, when you're doing all this GPU cluster processing, if you've got small models, they're all going to be confined to one node. But if you've got models that are huge data sets, you're going to end up having a giant cluster full of multiple nodes. And in that case, you're going to either be leveraging InfiniBand or converged Ethernet, on Ethernet networking. And so that's going to put a tax on there. And it's also going to create additional bottlenecks at certain places. And those are some of the things we're going to talk about here as to the why we need to think about this. And so the first one here is, if you look at a GPU data flow where RDMA is not involved at all, you're going to notice that on the worker one, it's gone from the GPU into CPU, then memory, and then back to the PCI switch, and it goes out that network card. And then it comes into the network card on worker two into the PCI switch, and it goes into the CPU and into the memory, and then back out of the memory to CPU to the PCI switch and into the GPU. You're already thinking to yourself, that's pretty inefficient, and I would agree, it is. And I'm going to speed this along here, and you can see what you end up getting when it comes to main system memory and the CPU on a node is you're getting a bounce buffer, because the GPU has to transmit all of its data first into main memory, which is going to use CPU cycles, and then it's got to come back out and across the NIC card. That's inefficient. It's also taking up CPU resources and memory in your system that could be used for other processes to run on those worker nodes. We can see the same process when it comes to actually talking about data flow. So in this example, if we're talking about NFS storage, we've got to go through the same process. We have to go from the GPU back into the CPU, the main memory, and then back out to the NIC to our actual storage. Again, it's a very inefficient pathway, and it does create that double bounce buffer that we see up here in the memory and the CPU location. So what is RDMA? Well, RDMA basically is remote direct memory access. It allows the computer's network adapter to access the computer's memory directly, and that bypasses the CPU. This is just vanilla RDMA, keep in mind. And what it leads to is lower latency, higher throughput, reduced CPU utilization, and reduced overhead. The CPU cycles aren't there as much because we're sending that data directly to the NIC from main memory. So if we look at the same flow now with just RDMA, we notice the GPU goes from the PCI switch to the CPU, and then it goes over to memory, and then memory back to the PCI switch directly, and then out the network card. So you'll notice from main memory, it goes right to the PCI switch and then the network card. And the same thing on the inbound, it goes from the network card to the PCI switch and into main memory. That's RDMA in a vanilla format. I'm going to speed this along. And so you can see we don't necessarily have the bounce buffer anymore, but we've still got some inefficiencies because we're still dealing with memory and CPU up here, when really all I want is my GPU data from worker one to go to the GPU on worker two. We can also see this again with the GPU data flow for NFS. Again, it's going to come out of the GPU up to CPU, into memory, memory directly to the PCI switch, out the NIC card into storage. So again, we're going to see some benefits here from speed, lower latency, but I think we can do better. And with that, that's what GPU Direct RDMA promises. And so with NVIDIA, what they've done is they've designed it so that you can go directly from the GPU out the NIC card and into the NIC card on the other node and into the GPU. That provides even lower latency and even higher throughput, further reduced CPU utilization and further reduced overhead. Because now we're not touching really anything with the CPU on that system, and we're also not touching anything related to the main memory of that system. And you can see that in this flow diagram. This was the original one that we saw, both without RDMA and with RDMA, but you notice now with GPU Direct RDMA, our flow is basically right across the bottom. We've negated the CPU and the memory of the system that we're running on, which again, frees up those resources for other things that we could do on that node. With GPU Direct Storage, which is another component from NVIDIA, we get the same benefits. We can go right from the GPU, out the NIC card, and into our storage. In this case, the example is NFS. I myself have tested with NetApp and have seen that benefit. There are other storage vendors that are supported by NVIDIA, but the NetApp one seems to be the most prevalent one out there when it comes to NFS. GPU Direct Storage will also work with NVMe local inside the system. The only difference would be here is that when the data leaves the GPU and goes to the PCI switch, that PCI switch is going to write it directly to the NVMe instead of going out the NIC card and going to storage that might be remote. And so when we think about the considerations for RDMA and GPU Direct RDMA, we have to think about the protocol. Like I said, some customers are going to do RDMA over converged Ethernet because they may not have an InfiniBand infrastructure, and InfiniBand can be costly at sometimes. And there might be customers who would use InfiniBand because, hey, they may have had HPC clusters using InfiniBand, and now they want to reuse that infrastructure for a more modern day approach using OpenShift, and then doing RDMA over InfiniBand. The other big thing that you're going to need is high-speed switches. When you're trying to move large data sets, we're not talking about the standard, 25, 50 gig, 100 gig switches. We're really looking at high-speed switches that are 400, 800 gig. The ones that NVIDIA usually would recommend are their Spectrum X line. That's not to say that Juniper doesn't have their, and Astra don't have their own switches that also do 400 and 800 gigs. So it really depends upon the vendor you want to go with, probably based on what your organization is already working with. For some shops, if they've already decided Juniper is the way to go, they may want to use Juniper high-speed switches. I will point out that these tests, these RDMA tests and GPU Direct RDMA tests, they will work over standard switches. You just don't get the performance. I've done them across a Juniper 25 gig connection, and you can test and validate that the RDMA protocol and stuff is working. It's just that you don't see the high speed data transfers that you would if you actually had the 400 and 800 gig pipe. On the host side, there's things to consider. Whether you're using RHEL or OpenShift, you really have to focus on the GPU Direct RDMA as a combination of the network drivers and the GPU drivers working together in order to transfer that data from the GPU directly to the NIC card. Some other things to consider is maybe the use of NVLink, where you've got all the cards inside of, or all the GPU cards inside that system linked together with kind of like what I like to think of it as a little ribbon cable that connects each and every card, so that instead of going through the PCI bus, those GPUs can communicate across those ribbon cable links. And then the network cards that you're using here. In this discussion, when we talk about GPU Direct RDMA, these are all Mellanox cards, because that Mellanox are the cards that NVIDIA uses, and it's what is supported for GPU Direct RDMA. Don't get me wrong, there are other opportunities when you're using AMD to potentially do RDMA type behaviors and activities, but those will be different than what we're discussing here today and how you approach those. And then finally, validation and testing tools are important when you're considering this. So a lot of times people will deploy their infrastructure and they want to go ahead and they want to throw their workload right on top right away. I advise you pause that step and go ahead and try to do some validation first that your infrastructure works. That way, when you go to run your workload, whether it's OpenShift AI or Slurm or some other software that you're using, you know that your infrastructure underneath is sound and that the communication is working between those nodes. And so if you're having a problem with the application, 9 times out of 10, it's the application that is misconfigured versus your infrastructure, is the problem. If you try to do all of this together, deploy everything, throw your app on there and nothing's working, how do you know what part of the layer is broken? So my validation and testing is the big thing that I would do before slapping on the application.
So Ben, do you think that is the RDMA over converged Ethernet, is that like the most likely approach that most people are going to? Is that, I guess, the most common approach that you see people taking?
For most of the customers that I've seen where we've had questions and I've had to work with, the primary usage has been Rocky, and that's because obviously it's cheaper to do Ethernet than it is to do InfiniBand. I've only had a couple of customers where InfiniBand was involved. So I mean, yeah, right now the consensus is RDMA over converged.
Okay, awesome.
So this is probably the last slide we're going to look at, and then I'm going to go away from slides because I'd rather have us actively look at the setup of this, and that's really what the rest of the slides in this deck would cover anyway, so why not just do it live? But when we're talking about enabling OpenShift for GPU direct RDMA, there's really these 4 components come into play. You've got to have an installation of OpenShift. You've got to have the node feature discovery operator on there, and you've got to have the NVIDIA network operator, and you've got to have the NVIDIA GPU operator. If you get all these things lined up with all the different caveats, and those are some of the things we'll talk about as we're showing the demo, that will get you the infrastructure that you're going to need in order to have GP1 work to talk other GPUs on other worker nodes. So with that, I'm going to back out of here, and I'm going to jump over to an OpenShift cluster that we have. So this OpenShift cluster is running 4.20.11. Just some kind of housekeeping to show where we're at and what we have. I'm going to jump down to nodes here. This is a 5-node cluster. I've got 3 nodes that are actually virtual machines running as my control plane. Those are the 3 nodes at the bottom of the list here, the NVD, SRV 43, VM4, 5, and 6 nodes. And then I've got 2 physical bare metal nodes. They're Dell R760XAs. And those 2 bare metal nodes have a couple of GPUs in each of them, and they've also got some Mellanox CX7 cards in them. One CX7 card is configured for Ethernet, and the other one is configured in InfiniBand mode. This particular test harness that you're seeing has the ability to do both InfiniBand RDMA and also Ethernet GPU direct RDMA. And if we have enough time, I'll be able to show both options in flight. But that's kind of the lay of the land for this. One of the first things I guess I want to point out when talking about, I mentioned that OpenShift is a key part of having this deployment. And so when you deploy OpenShift, you can deploy it any method you're comfortable with. So whether it's agent-based installer, assisted installer, if you like the old IPI or UPI installation methods, you can do that as well. I think the key here is to make sure that you've got nodes that have GPUs and Mellanox cards in them. The other thing that I did do ahead of time, because I didn't want us to wait for the reboots of machines, is depending upon the nodes you're using, you may have to blacklist certain kernel modules. And the reason you're going to have to do that is because they may interfere with the network operator when it goes to unload the in-tree drivers for the MLX drivers and then load up the out-of-tree drivers that it compiles on the fly for the MLX cards. And so what I did here is there's a machine config in this environment, if it'll catch up with me here, that blacklists the IRDMA module. The IRDMA module usually is only loaded on systems that, at least where I've experienced it, on systems where you've got an Intel 810 card or any Intel card that can potentially do RDMA. When the IRDMA module, or when those cards are present, RCAS by default is going to load this IRDMA module. We're not going to need it for the RDMA work that we're doing with the NVIDIA cards. And so we need to make sure that that stays unloaded. If it is loaded, what ends up happening is that the network operator tries to unload drivers, and it can't unload the some of the drivers that are dependent on IRDMA because there's a relationship there. And so it'll cause that deployment to fail. And then you've lost all your network adapters when it comes to the Mellanox cards because it's unloaded the MLX drivers, but it can't reload the new drivers because of this. And so this is documented in our official documentation as one of the things you want to be aware of. But in the case of these Dell boxes, for example, I know that it's already that IRDMA will load up. So I go ahead and I blacklist it, and that way the module's not there. And I do that as just a step for my installation of OpenShift. Another recommendation that I like to make, but you don't have to do it, is I like to set a core password on my worker nodes just in case. And the reason that I say just in case is early on with some of the network operator work that we did, when we only had Mellanox cards in the box and we went to do the deployment of the network operator, when we ran into situations where the drivers didn't load properly, now our box was completely network dead. And if we didn't have a core user password set, we couldn't log in via the console and actually take a look around. And so I like to have it set just in case. That way I'll be able to do that and check on things to troubleshoot the problem without actually having to try to repeat it. So again, it doesn't have to be done. It's just a suggestion, but it's one of the things that I do as a practice just because of previous experiences.
So Ben, before we move on, like with the password, how do you set the core user password?
I use a machine config to do that, and I don't think I did it in this environment. But literally what you have to do is you have to create a hash, and then you take that hash and you embed it in a configuration file. I'm just trying to see if I did set one here or not. Oh yeah, I did. So there you go. And I did it for both the masters and the workers. In this example, it wouldn't even need to be on the masters because we're not doing anything with the masters that applies. But yeah, it's basically just a simple machine config. You create the hash and then you embed that hash in the file here with the username core, and there's the password hash, and you go ahead and apply this, and then that allows you to go onto a console, via like an iDRAC in this example, because it's a Dell box, and I could say
absolutely
password, log in. I can now look around and see, if I did an IP link, I can't see any of my devices. Let's do an LS mod. Yeah, my MLX drivers aren't loaded. That tells me the reason why my interfaces aren't there. Let's go look at the pod logs on this box just to see why didn't they load. If you have set the debug, and we'll get to this further down in the conversation here, but if you set the debug logs, 9 times out of 10 you'll be able to see why it didn't load. In those logs, it'll tell you. A lot of times it's because there's a kernel module in use. In the case of if IRDMA was not blacklisted, we would see that IRDMA is in use. It can unload it. That's the reason why it failed. But yeah.
So are you doing this? I'm sorry, I'm sorry about that. When you're applying these, are you applying these after you've installed your cluster, or are you, like you can do like the OpenShift install, create manifests? Are you like adding these manifests into your install directory and then deploying, or is this like a day zero type of config? Like once you've got the cluster up, now I'm going to apply this, let it roll out, and then I'll start doing my extra stuff.
I've always done this as a day 2, but does it need to be? No, it could be. You could set this into your manifests for your day 0 on your deployment. But I've always just done it after the fact. Because sometimes I don't. Sometimes I don't always do it, and sometimes there's not a need to. For example, on the IRDMA one, if I have a server, like if I have a super micro box and all the cards that are in there are Mellanox, I know that the IRDMA module is not going to be a problem there.
Right.
So there's no need to even apply the machine config. But, would it be a problem if you went ahead and applied that machine config anyways? No, it wouldn't affect anything. It'd be fine. But I always do these day 2, just because I don't know what I'm going to apply or not apply.
I like it, man. I've never, not that I didn't think about it, but I've just never had to, I've just always like, all right, I'm just going to burn it down when my nodes became unreachable. So I love this idea. This is actually a really great idea.
The other thing to keep in mind is when you do run into that situation where you've applied the NIC cluster policy and all your interfaces are gone, the backout for that is always to go ahead and remove your NIC cluster policy, because your control plane should still be up and operational. So you remove that NIC cluster policy, and then you go reboot those nodes. And what'll happen is when they come back, they initially come back with the in-tree drivers. And because there is no NIC cluster policy to tell them, oh, you should unload those and load the out-of-tree drivers, they'll come back normally and they'll behave normally until you try to reapply your NIC cluster policy.
Okay, awesome.
So, and we can talk more about that when we actually get to the NIC cluster policy part. I'm probably getting ahead of myself. So what I want to do first here is I did do a couple of other pre-baking steps just so that we didn't have to wait for certain things. Because some of these things are really basic. And so I figured let's just do them ahead of time. And so what I did do is I installed the operators that were going to be necessary for what we're going to see today. And what I mean by install the operator, I literally mean I went to the software catalog, I found my operator, I clicked install. There wasn't anything special about the configuration yet because we're going to do the configuration piece secondly here. But I went ahead and I installed the GPU operator because we needed that. I went ahead and installed the NM state operator only because when I deployed this cluster, I did not set the Mellanox interfaces with an MTU of 9,000. And so they ended up getting a 1,500 MTU because the switch ports on the other end are on 9,000. I wanted to rectify that. So I figured I would just use a node network control policy to do that, and that's what I did, and that's the reason why NM state is installed here. So this is an optional piece that you don't necessarily need, but you understand the reason why I went ahead and did that for my goal.
Do you mind showing that?
The policy?
Yeah.
Yeah. Let me see here. I'm so used to doing all this stuff from the command line that I don't usually do.
I know. I'm sorry to put you on the spot. Like, I'm the same way, dude. I struggle in the UI.
Yeah, so what I did is I created two of them, one for each node. And again, I tried to do it across all nodes, but then that wasn't working because it was failing because it couldn't find the interface in my master nodes, which makes sense. Those are VMs. I have no Mellanox cards in them. But anyways, on each one of these, I just went ahead and basically put in a description of what I'm doing. Here's my Mellanox interface, the EMP55, and the MTU I wanted to set. I'm setting the state up in Ethernet. There isn't anything more you need here. Now, if I wanted to configure an IP on this interface, sure, I could have added the IP information in here and stuff like that, but all I really wanted to do was switch the MTU to 9,000.
Nice. Perfect. No, I just wanted, it's just really for clarity on everything. No, I appreciate it. Thank you. This is awesome.
No, I mean, I love this. If you can ask more questions like that, this is great because then it'll call out all the things I might skip. So let's jump back real quick to the installed operators. The other ones that are listed here, node feature discovery, so NFD, we need that to label the nodes to tell us, that they have Mellanox cards, that they have GPUs, because that's what the NVIDIA operators are going to look for, are those labels, and that's going to determine when the pods spawn. And then the NVIDIA network operator. What you don't see here, but could be an optional need, is if you want to use this setup in a SIROV scenario. So when it comes to doing RDMA with GPU Direct, you can do it in basically three different methods. You can do RDMA shared, which is what I'm going to show as an example of today. You can also do SIROV, and that means what you're going to do is you're going to take those NIC cards and you're potentially going to carve them up to multiple VFs, and then those VFs could be passed up to different containers or pods in your environment. And then there's another one called host networking, which is where you're literally passing the full interface up to a pod. Some of the reasons why you might use that host networking one is maybe you just are going to have one single pod on the node, and you just want to pass all your NICs up to that single workload. SIROV becomes more attractive. You're going to have multiple workloads on there and all need to have access to the NICs. It also allows you to do some granularity. Maybe one VF is on one network and one VF is on another one. So you get that segmentation that you might need there, especially if you're thinking about maybe, multiple tenants. And then RDMA shared is basically a real easy way where we can take the NICs and we can share them amongst many pods. So in this example we'll see today, I've got two interfaces, and each one of those interfaces could have up to 63 pods shared amongst them. That 63 number is a number we'll configure in the network operator. Again, getting ahead of myself. So let's kind of back up here and go back to what we need to do now. So the operators are installed. We need to go ahead and configure them. And so the first one that I'm going to do is this node feature discovery one. What I really need to do is create a node feature discovery instance here. And so I'm going to go ahead and click on the create one, but I'm not going to use the one that's there. The one that's there should work for us, but I'm kind of a creature of habit. And so I always use what I know is going to work for me. And so I'm going to paste in this one, which basically defines the device class whitelist for the NVIDIA devices that we're interested in. So I'm just going to, if it catches, yes.
We got a quick question. So Alan asked if the question is, so it's required to have enum state and NFD, right?
NF state is optional. NFD is definitely a requirement.
Cool. Thank you very much.
Yep. So I've gone ahead and I've pasted in the NFD node feature discovery policy that I've always used. Like I said, the only big difference here is I've defined my device class whitelist. Those device numbers are all related to NVIDIA Mellanox and or GPUs. And this has always worked for me and the reason why I do it. Like I said, the default should probably work for you. So you could go ahead and use that, but I love sticking to what I know works.
100%.
So I'm gonna go ahead and click create here, and that's gonna go ahead and do its thing. What I like to do is I just like to go over to pods and see that all my pods for NFD get created. And if I see that, that usually lets me feel comfortable about moving on to the next step here. And so, yes, we can see that we've got our two worker processes are showing up on the worker nodes and the master's running and the controller's running. So we're good to go. So that really is all there is to doing the NFD portion. What you should see if it worked properly is when you go to nodes, if we clone on one of these bare metal nodes and we go into like details, and I'm just going to quick do a find here. We should see a label. I think it's like 15B. Yeah. So here's an example. Like the node feature discovery told me that my Mellanox cards in here, they're SIROV capable. And that's a true statement because in the firmware of these Mellanox cards, I have turned on SIROV. I've enabled 8 VIFs per card. We're not going to be showing that today, but again, this is showing you that the NFD labeling did properly happen because the nodes got labeled with the information that's going to be important for us when we deploy our network operator and we deploy the GPU operator. So I feel very confident that we're ready to move on to the next step. And so the next step in this process then would be to install or configure the network operator drivers. And so like I said, we installed the operator. What we actually need to do now is configure a NIC cluster policy. Now this NIC cluster policy is really going to define what do we want to do for the network cards on this node. And there's a form view here, and there's also a YAML view. I've always just used the YAML view, and I've always done this at CLI. I usually don't do it in the interface. The default here is most likely not going to work for us. There's a couple of things that are missing, and so I'm going to paste in my own version, and then I'll point out the reasons why my own version is going to work for us better. One, it's got the right interfaces for this particular system. So I'm just going to go ahead and grab all this and paste in my new one. And so let's just start at the top and kind of walk down. So in the NIC cluster policy, we've got a spec section, which is the OFED driver. That is the actual MLX drivers. And so what the network operator does is when you launch this NIC cluster policy is it will go and it will look at the kernel version that's running of RCOS on this box. It will launch a driver toolkit container. That toolkit container will then build these out-of-tree drivers based on the kernel that you are running on the fly. And then it will take those drivers and it will unload the in-tree drivers and it will load these ones that it compiled. That's what's going to happen. And so in here, much of the defaults can stay the same that you're seeing. One of the key things is your driver version. Depending upon what you're trying to do in your environment, that driver version might change. Usually the default will work. In this case, I am using the default driver. What I want to point out are these environment variables. And this was the part that wasn't included in the original YAML that showed up when we went to create the NIC cluster policy. What I've found, at least on these Dell systems, is that if I don't have those first 3 environment variables, unload storage modules, restore driver and pod termination, and create the IF names UDEV, the NIC cluster policy will not deploy properly, and it will fail. And so I just automatically throw those 3 environment variables into my NIC cluster policy, no matter what kind of hardware I'm deploying it across. The 4th one listed there, where it says enable NFS RDMA, that is if you intend to do GPU direct storage against, a NetApp or a Weka IO cluster is another one I know they support. I think Pure Storage has another offering that uses 1FS, so it's another NFS scenario. But if you want to use GPU direct storage, you have to have that environment variable in this NIC cluster policy, or otherwise it's not going to work when you get to that point of actually trying to mount an NFS volume via GPU direct storage. And then finally, my favorite one is the last one, the entry point debug. I would just include this all the time. What this is going to do is give you the debug logs for the MoFed container. It's very insightful, especially if your NIC cluster policy does not deploy properly. Having the debug turned on is not going to generate logs, hundreds and hundreds of logs, because the logs only generate when it's actually doing the process of unloading the driver and all of that. Once that's all done, the container basically goes into sleep and doesn't generate any more logs. And so having this on will make it much easier if you have to have a conversation with support or have a conversation even with me, because I'm always going to ask you, well, do you have debug logs? Because those usually show us the detailed information we need to see.
So Ben, real quick before you move on, Alan Caldelas had asked, so don't you get specific labels from OpenShift virtualization? Basically asking what label is actually required specifically for or from NFD, and then the follow on is he thinks that it's kind of odd to have NFD to work with NVIDIA network operator. Couldn't it just install it for us?
So if I understand that question properly, why do we have to have the need for NFD, correct?
Right. And which label are you specifically using from that to, which label are you using specifically from NFD with the network node operator?
I think it's a combination of things, and I don't know directly off the top of my head what they're looking for in their code, but there's specific things that NVIDIA put in their code that's looking for labels on the node. And so without NFD, you won't have those labels. Could you manually put those labels on there, which I think is what his question really is getting at. It almost sounds like he wants to just do that manually. You probably could. We would have to get you a list of those labels outside the scope of this call if you really wanted to have that information. I guess my rebuttal on that would be more about why couldn't you have NFD? And maybe there's a security reason for it. I don't know, but I guess NFD is doing a lot of the heavy lifting for you and ensuring that the labels get placed on the node so that you don't have to worry about manually creating those labels. But if you don't have those labels, when you go to run the network operator, it's going to think that you don't have anything to install a NIC cluster policy on. And so none of the MoFed driver pods are going to spawn. And I've seen that where NFD's been misbehaving. If NFD is misbehaving and didn't do its job, and then somebody goes to do a NIC cluster policy, it doesn't even deploy anything. And so you're left scratching your head, well, how come this isn't running? I know I have Mellanox cards in the box, but it's because NVIDIA's code isn't seeing the labels it's expecting on those nodes. And so now it doesn't know what to do. And it just says, okay, we've created the NIC cluster policy, but there's no node to apply it to.
Got it. All right, Alan, hopefully that answered your question. If not, feel free to add a follow on.
Yeah, we can always do a follow-up on that. So now let's jump down here to this RDMA shared device plugin. So like I said, we're going to do RDMA shared device today. If you were doing SIROV or host device, this section would not necessarily be in this NIC cluster policy, but because we're doing RDMA shared, you have to have this in here. And the setup that we're showing here, and I'm trying to get both of them in frame, is I'm showing that I'm going to share 2 different devices. One device is an IBP13, so that's my CX7 in InfiniBand mode. And the other one is ENP55, that is my CX7 in Ethernet mode. And you'll notice that they've got that RDMA HCA max. By default, NVIDIA has that number at 3 or 63. What you need to think of that number as is that's the number of pods that can consume this shared resource. So when the actual resource name shows up when you do an OC describe nodes, and it says RDMA shared device IB or RDMA shared device Ethernet, you're going to see that there's 63 allocatable. Now, could this be more? Yeah, I could change that number to 100, 200. But just think about it. If I'm sharing a single device, as this example shows, and now I've got, instead of 63 pods, I've got 100 pods or 200 pods, they're all sharing that same interface and competing for the bandwidth. So those are just the considerations you have to take in. But that number 63, it's an arbitrary number. You can increase it, decrease it. You can do what you want. I've always left it at the default. But if you only really knew that your system was going to have maybe 2 pods running on a node, you could leave it at 2, and that would, suffice. But this is, again, where we're defining the sharing of those 2 interfaces. This is one way to show this. You can also use your selector, and you can select it by a device. So I could just say, hey, I want all of these devices inside of the box that are Mellanox, and you could put in the device number. I want all of them to be shared as a resource of RDMA shared device IB or RDMA shared device Ethernet. My example, I use 2 interfaces. I've only got 2 cards in the box, and I wanted to show both the InfiniBand and the Ethernet. And then finally down here, we've the image for the RDMA shared, which is a NVIDIA image that gets pulled, and then we've got secondary network images. So we've got this CNI plugin, which also comes from NVIDIA, and then we've got the IP over IB. That's to allow our InfiniBand interfaces to work inside the pod so that they've got an IP on the inside of the interface, but really that connection and the communication between my pods on different workers is going to be over InfiniBand. And so with that, I'm going to go ahead and create this. And this is going to take just a little bit to deploy. Usually it takes about 5 minutes, to be honest. And that's one of the reasons why, is because there is a timer inside the MoFed pod that basically wants to wait 300 seconds. And so because of that, let's just kind of go in and look at the logs of that. And we can watch what's happening. And you can see, it says awaiting OpenShift driver toolkit complete NIC driver build next 300 seconds. So there's a 5-minute check. We can go over and look at the toolkit and see what's going on in there. And we can see that it's already executed the command to actually build the driver, this install.pl command. That's generating another log that doesn't actually show up in the pod log here, but it's available if you actually go into the pod and look under the temp OFED. You can see that general log. I personally have never had to go in there and look at that log, so it's not something that usually fails. But again, this is building the drivers for our kernel version that's currently running on this system.
That's awesome.
I'm going to point out one other thing, since we've got a little bit of time here to wait. If I do go into the MoFed container, I want to point out, I think we can see it from here. Maybe not. So let's jump to a different spot. I thought we could see it there, but we can't. I'm going to go on to one of the nodes. And what I want to show is where these drivers are being stored and built. Because the way NVIDIA set this up is they basically use the driver toolkit to build the drivers, and then that lands the data on a disk location of the host. And then the other container mounts that location and installs the drivers that way. And so if you go under op, oh, look at that. I'm getting ahead of myself. If you go under opt, you'll see there's this MoFed container, and under there's an inventory, and under there's this kernel version directory. That kernel version directory happens to match the kernel version of our cluster. And if we go under there, we can see there's another directory. And if you eventually get into it, there should be drivers under here. But the idea is the drivers should be here once they're finished being built. And then this is picked up by the other container and consumed. Now, one of the things that I recommend is if you do have driver failures with the NIC cluster policy, one of the things I like to do on cleanup is remove the MoFed container from the systems before I redeploy. I also might do that if I'm testing different versions of the the Docker driver from NVIDIA. So again, not necessarily something you absolutely have to do, but it's kind of one of those things that if I'm doing a lot of different testing with different versions of the Docker driver, I'm always going to come in here and remove this directory before I reapply a new NIC cluster policy. So you may or may not need to do that, but it's just one of those things that I point out.
So have you done like upgrades from like 419 to 420 to, well, not 421 yet, but like, 418 to 419 to 420. And then with that, like has the NVIDIA driver updated along the way? Or like, do you have to wait for a specific release of the NVIDIA operator to drop before you make the update? You know what I mean? Because I know back in the day there was an issue with like I think it was a GPU operator where it was it was almost bound to a specific version of OpenShift, and it would have to be rebuilt literally almost every time. It was early days though, so I'm sure it's probably much more streamlined.
So what I have directly experienced is just upgrading the RCOS underneath on a version of OpenShift. So going from, let's say I'm on 420.0 and it's got an RCOS version. We'll just use simple numbers here. It's RCOS version 1. And then I go to 420.10 and that has a RCOS version of 2. There's an update, right? And the kernel version changed because part of that update contained a kernel update. What should happen is when the nodes come back up after the machine config got applied for those updates, is the NIC cluster policy should rebuild your drivers for that new kernel version, and then it should continue on as normal. And so you really shouldn't see any of that behavior. Now, to your point about when you go update for major versions of OpenShift, so going from like 420 to 421, 421 just came out, right? Well, guess what?
Yep.
The 421 version of the network operator is not there yet. That'll be coming mid-February. And so you'll probably end up running on the old driver potentially if you do upgrade to 421. And so my thought would be is I would wait to upgrade your cluster. If it's using the network operator, I would wait until the next version of the network operator comes out for that version of OpenShift. So in the case of 421, I would not upgrade to 421 until I see the 2610 release of the network operator, which, like I said, is supposed to come out about mid-February sometime.
Gotcha. No, that's solid advice, man.
So as you can see, as we were talking, the MoFed containers eventually went to a 2 and 2 ready. So we know the drivers got installed, and then our RDMA shared plugins came up. So we're looking good there. I'm just going to jump into this MoFed pod one more time because I want to show you, I want to scroll back through this or scroll forward through it, I guess, and just show you trying to see where the best spot in here is to show that things were fine. You can see a lot of these exit codes are 0, so that gives me a good indication that things are good. Yeah, I think I was just kind of showing you this is what a normal log should look like. We don't have a failure here, so there isn't anything really exciting to see. And then notice the container went to sleep infinity. So again, I have debug logs, but I'm not generating tons of logs anymore. I'm done generating logs until this has to rebuild for, in the case of a kernel upgrade, for example, then we would generate a new section of logs because there's an update, it has to recompile the drivers. So now that we've got the network operator installed, let's do the last piece of the puzzle, which is the GPU operator. And the reason that we do the GPU operator last is because if you have RDMA enabled in the GPU cluster policy, it's going to wait for the MoFed containers to be done installing. And so you have to have the NIC cluster policy deployed and have that stuff deployed before you can actually go ahead and do your cluster policy here. So with that, I'm going to go ahead and create a NIC cluster policy. Again, this setup has a form view if you want to go through the form view. It also has a YAML view. I'm going to paste in one that I've already pre-configured for this environment and talk to the specifics of what's special about it. So just let me grab that.
And Ben, would you be willing to share these configs after the fact? I can post them in to adjust and then share them out through the the stream notes.
Yeah, absolutely. The other thing that
Okay.
people they can take a look at is they can take a look at a few of the personal blogs that I have out there that talk about GPU direct RDMA. And so it's a very similar scenario to what we're doing today, except it's all via CLI instead of the GUI. And they also has a blog about GPU direct storage as well, which shows the example that I did with the NetApp. So the information is out there in multiple spots when it comes to my name. So, however people want it, if they just want these raw YAMLs, we can get them the raw YAMLs. If they want some context around all these YAMLs, they can go look at those blogs, and it really provides you a step-by-step walkthrough in how to do this. Again,
Perfect.
the only thing that's changed from that blog is the versions of OpenShift and the versions of the network operator. So, and that's just with time. So,
Yes.
like I said, I went ahead and I pasted in my version that I wanted to use. Here's the things that are I'm going to point out that are from a non-default perspective. The CDI enabled currently, NVIDIA has defaulted that to true. I set it to false. I've seen it where sometimes if it's set to true, it creates this CDI hook error issue. So I'm just setting it to false here so we don't necessarily see that error today. The other thing is the kernel module type is set to open here. By default, NVIDIA leaves it at auto. Open was always the method that we were supposed to use with OpenShift. The auto is supposed to auto detect, and it should use the open kernel modules. Again, it's just a habit for me. I like to use what I know works. So I set this to open always. Auto should work in here though as well. And if you hover over it, it seems to tell you what options are available. RDMA enabled, I set this to true. Now, this one is interesting because does it need to be true? Not necessarily. So by setting it to true here, what's going to happen is the NVIDIA GPU operator is going to compile a driver called the NVIDIA PeerMem module. That NVIDIA PeerMem module is going to be one of those driver components that lets the GPU talk directly to the NIC. By setting this to true, so you can compile that module, it's anticipating that the network operator has already been deployed and the NIC cluster policy and everything is already deployed, and those drivers are built over there because it's going to need some of that as well to do this. Now I say, does it need to be set to true? Not necessarily, because if you set this to false, you can still do GPU direct RDMA. It will just fall back to using DMA buff, which is built into the kernel. So NVIDIA has said they would prefer people start to use DMA buff. I have not seen official writings of that in NVIDIA documentation. So I try to just point out, you can go either way here. If you're going to do true, make sure the NIC cluster policy is installed and running. If you're going to do false, you in theory could deploy your GPU policy before your NIC cluster policy, because it's not going to need that dependency if it's set to false, because it's going to use DMA buff built into the kernel. So again, you can go either way here. It's a preference. I left it at true here today just to show. And so that's
Can you go back up to your driver licensing config? Does that need to be set? That was from Alan.
That's a default. And true is default. So that's the way it is. I've never had to do anything with licensing when it came to this. I think where licensing comes into play more so is when you're talking about virtual GPUs.
Okay, that makes sense.
So yeah, Alan, that is a default that comes, so if I went back and did the form view or did the YAML that was already here, that would have already been set to true. I've never messed with that. So from my perspective, that's just a standard that they have. The other thing I want to point out is GDR copy. This allows memory of the GPUs to exchange. And so I always set this to true as well. By default, I believe it's false. But again, I've always used it as true. And the one thing that's not in here is, and because we're not going to demonstrate it today, was the GPU direct storage. But if you were going to do GPU direct storage, there should be a spec location, which would be called GDS. And then you would have, in the GDS, you would have it enabled as true. The big thing about GDS is that if you do have it enabled to true, NVIDIA is expecting you to provide the GPU direct storage image location from NVIDIA's repos. And for me, that's always been a hunt to get that information. I don't know why they don't just have the GPU operator populate that directly, but maybe not a lot of people are using GPU direct storage yet. But that would be another section in this file that we don't see because we're not demonstrating that today. And the rest of this is all defaults. Oh, here's the GDS, and it says enabled false because we're not doing it. And like I said, there'd be a few other lines in here to show the image location if it was enabled for true, that you would have to self-populate. So I'm going to go ahead and I'm going to kick this off because it's going to take just a few minutes for this to create as well. And so while that's kicking off, I like to go watch the pods over here, especially if it's my first time doing this on a system I've never done it. But you can watch all the things that are kicking off, and it's going to take just a few minutes for this to deploy.
Do you know, do all of these operators, like the GPU operator and then the NVIDIA network operator, do they all support disconnected or air gap? Well, basically, do they all support air gap environments?
They do. So when it comes to air-gapped environments, like with the network operator, for example, there is a process where you pre-compile the drivers so that you end up with the RPM packages, and then you would take those packages and you would push them into your disconnected environment. The other option would be to ensure that you have mirrored all of the requirements that the network operator would need to build that stuff on the fly. You'd want to have that available somewhere inside your disconnected environment. And that's going to be a combination of a disconnected registry that would contain the images you need. And you would also need some of the repo packages, because when that driver toolkit container kicks off, it's got to pull in some actual RPM packages for Perl, because the NVIDIA compile script is a Perl script that they're using. And so that gets a little more cumbersome when you do that. So it's almost better just to pre-compile the drivers outside the environment and push those into the environment for consumption. But yes, there is a pathway to do that. And the same thing is true for the GPU operator, although I'm not as intimately familiar with the one in the GPU operator, but I think it functions in the same fashion. You can either pre-compile the drivers, or you have to have all of the things that you need for the requirements staged inside that disconnected environment.
Gotcha.
What I'm going to do while we're waiting for this is I'm going to create a couple of other YAMLs that we're going to need. One of them is the Mac VLAN network. So this Mac VLAN network is going to be for our Ethernet interfaces. And this is basically just a standard Mac VLAN network, although it's Mellanox version. So again, you got to have the network operator installed here. Notice that I've picked my interface, ENP55, the MTU set to 9000, and then I'm just using a standard 192.10 network here. In this example for my IPAM, it's a whereabouts addressing scheme, so the OpenShift cluster is going to be keeping track of that. And with that, you can define a gateway. So for example, if maybe there was an actual true gateway on this network, in my test here, there is no gateway, it's just a layer 2 setup. And then if you need to exclude for maybe other IPs that might be on that particular network, you can do that as well. But I'm going to go ahead and create this. And it already exists, huh? Oh, wow. Maybe I created that ahead of time. Let's just delete that, and then I'll recreate it. I'm just deleting it off screen so that you can see me create it via the UI. So let's try that.
Your keyboard is letting us know that you're doing something. So.
Okay, yeah, but you're not seeing the CLI value, right?
No.
And all I basically did was say OC delete -F in the name of that YAML at the CLI perspective. So nothing really exciting there to show anyways, right?
No, never.
All right, so I created the RDMA shared -net, which is pointing to that ENP55 network interface. Now I'm going to go ahead and I'm going to create one more, and this is for the InfiniBand interface. So this one's a little bit different, but very similar. In fact, it looks a lot similar actually, but it's the kind is what's different here. And so the kind is the IP over IB network. So again, this is where inside my pod, I'll have an IP address that's associated to my interface, but that IP address is going to get translated into an InfiniBand packet, which will then go across InfiniBand, because we all know InfiniBand actually doesn't know anything about IPs, doesn't know anything about, ARPing or any of that stuff, because InfiniBand is a completely different protocol compared to Ethernet.
Mm-hmm.
But again, I'm using basically the same network range and everything in here. And then my master interface is that IBP interface. Let's see if I pre-created that one. No, I actually did remove that one here. So that's created. So now let's jump back to the GPU operator and see if it's ready to go. And yes, I can see that everything is ready to go because everything is running. Things have completed. I don't see anything crash looping. We're ready to actually do a demonstration here. So we're still good on time, right?
Yeah. How about it?
All right, perfect. So now what I'm going to do is I'm going to go ahead and I'm going to create 2 containers. And again, I've got some pre-canned setups here that I'm going to use. Kind of like, we mixed the cake ahead of time. So now we're just going to go ahead and show you the finished cake, although this is going to require us to wait a little bit as well. So what is this doing? So a couple things that I've already done ahead of time. I created a service account yesterday on this box called RDMA. That service account I did give privileged access to. You don't necessarily need privilege to run these containers. I've just had that dirty habit of doing it. There is a way where you can skip the privileged part and still get the benefits of what I'm showing here. I can't remember that off the top of my head. So if anybody's interested in knowing that, that would be a follow-up. But yeah, by setting the service account and giving it privileged access, I've gone ahead and I've got a privileged container here that I'm going to run. Notice that I'm referencing this NVIDIA tools image. This NVIDIA tools image is an image that I have a GitHub repo that's publicly accessible. That image basically contains a lot of tools that are helpful when you're dealing with RDMA environments. Some of the tools that are packaged in there are the MFT tools for Mellanox cards. Those MFT tools allow you to flash the firmware on Mellanox cards. They allow you to look at the actual fiber connectivity of the optics on those cards. They let you make changes to the firmware. So for example, if I wanted to change the card from NIC mode to InfiniBand mode, or if I was running with a BF3, maybe I want to change it from NIC mode to a DPU mode. Those tools give you the ability to make those changes. The other things that are packaged in this tool container is perf test utilities, IB write commands, for example. I also package up the nickel or the NCCL NVIDIA tests as well in this tooling. So it's kind of like a Swiss Army knife of tooling. And the reason I did that was because every time somebody would come to us with, I want to run GPU Direct RDMA and I'm using this container, it was some container image I wasn't familiar with. So I didn't know if it was, the container's fault or if it was the environment's fault. And so I eventually built this image and we're using it. And even in documentation, we're referencing a version of this image. And so that way we've got a common set of tooling that we're using and working with, as opposed to some image that came from, I don't know where it came from.
Right.
And then finally down below, we've got the resources. So this is the key part is I want this container to have access to a GPU and one of those RDMA shared device Ethernet interfaces. And so that's why I've got those limits and requests down there. I'm going to go ahead and click create because we're going to have to create another one on the other node because I've specifically called out this is going to get created on node 29. And it's going to take a little bit to run. So I'm going to quick create that. And I'm going to show you the same config that we just did. It's only going to be for node 30 here. So if you have questions about the actual config, please ask, and if you want to see the config again, you're going to see it again, except like I said, the only thing that'll be different here is the node name itself that's referenced. So you can see nothing much has changed here except 29 is now 30 in 3 different spots. The other thing I guess I should point out is the annotation. You're going to need this up here under the annotations of which network you want to use. We're going to use that RDMA shared-net network. That was the one that we defined with the Mac VLAN that we just created. That was what we were calling it. So that's going to say we're using that network and we're using those RDMA shared devices. Again, I'm going to create this and let that kick off. I'm going to create 2 more containers while we're at it, since the first 2 will not be ready for us to consume yet. And I'll talk about that in a few seconds, but I'm also going to kick off 2 of them for InfiniBand so that we've got those running as well. And I just got to find them. So these will look very similar to the ones that we just did. I'll just point out the differences on this first one. So again, this is going to be launched on node 29. So the first difference is under the annotations for the networks. Notice we are referencing IBOIB network, which was the IBOIB network that we just created after we had created the Mac VLAN. So that's the name of it. So we're referencing that there. And then the only difference down below under the resources is that we're referencing the RDMA shared device IB network. So again, I want an InfiniBand interface on this pod. I don't want the Ethernet one like we just deployed on those first 2 pods. So I'm going to go ahead and create this. That one will get created on node 29. I'm going to create a counterpart on node 30.
Ben, I know you don't use the GUI very often, but I want to let you know that you're doing a great job. Like,
yeah, I really don't.
I would be clicking all over the place.
and you know, the reason why I don't use the GUI is because when it comes to writing, we'll go take a look at these blogs after this. They're going to see that I try to capture everything that I'm doing. And so if I did that in the UI, imagine doing that in an update, right? Like I got to do a new blog about the same thing. Well, now I've got to update all those screenshots because the UI has changed maybe. And that's the reason why I like to do it at the CLI. So it's not that like I hate the GUI, because I think the GUI is a great tool for anybody that's not familiar with OpenShift initially. I think it's a great way to understand how things work. It's also a great way to spot check things instead of doing it from the CLI. But from a documentation perspective, I think it's easier to update documentation from the CLI because you just have to go in and make those, search replace changes, as opposed to with a GUI. If you want to capture the GUI's true value, you've got to take screenshots, and then you're going to have to retake new screenshots. So I went ahead and I've created all the pods now, all under the default namespace. And I went ahead and did that ahead of time because, like I said, it's going to take some time. So I'm going to show the last pod we just created. I'm going to go into logs. So this container has an entry point script that runs. And what that entry point script is doing is it's actually installing all the components we need. I don't ship NVIDIA's components in my image. Red Hat has always been good about not shipping third-party stuff in their product. And so I took that to heart. And so in my container, I don't ship any of NVIDIA's binaries or anything like that. What I do is I have an entry point script that goes out and grabs that stuff when we launch the container. So what does it grab? It grabs the MFT tools and it installs those. It grabs the MLX-UP, which is another way you can update firmware. It grabs that binary and brings it in. It goes and it installs the CUDA libraries because the CUDA libraries are required for the NCCL tests. It then goes ahead and grabs the GitHub repo for perf test, and it compiles all the binaries there and generates the IB write commands that we're going to demonstrate and use here. And then after that, it goes and it pulls the GitHub repo for the NCCL test, and it builds and compiles those as well. So the image is very lightweight in the beginning. And then once you go to run it, it starts to pull in all of this information. So somebody out there is going to ask, well, what do I do if I'm in a disconnected environment? I haven't thought about that from that standpoint as far as how you would do this. But if you were going to do this in a disconnected environment, you'd have to basically take my GitHub repo, which shows you how to build this image, and you'd have to retool it to point the places that it's going to grab the things that it needs to a local location inside that disconnected environment. So you'd have to basically recreate my image, but tool it to the fashion for that disconnected scenario.
Yeah.
So let's go back to the original 2 pods that we created, because those might be ready to go. And then I can actually demonstrate something and we can feel like we've learned something here today. So let's look at the logs first. This is still going, but where it's at, it's doing the NCCL stuff. So it's gotten past the IB write commands, which are the things that I want to use in my demonstration. So I think we're ready to go ahead and try this. So I've got the terminal open for node 29 here. I'm going to go ahead on this other screen, and I'm also going to open up terminal 30. So I want to have 2 screens, one on each worker node, because the goal here was to show traffic transferring between 2 different worker nodes. And so I've got 2 pods, 2 different worker nodes. Each of those pods has GPU assigned to them. In fact, let me just show you that really quick. You can see we've got a GPU over here. It's an L40S. It's not the top of the line. It ain't no Grace Blackwell, but hey, it's going to serve its purpose for what we're trying to show here. And if we go back over to here, we can also see the same thing. We've got an LS40. So we're good there. So one of the first things that I need to do is I need to identify a couple of parameters here. And so there's a script that's included in this image called show gids. If we run that on this box, it's going to tell us what we're interested in knowing for our IB write command. And specifically what we're interested in is we want to know what interface has the IP addresses assigned to it. In this case, it's a device MLX5_1 with the IP address of 192.168.10.2. And you'll notice that there's 2 of them. Why is there 2 of them? Well, one is version 1 of Rocky. The other one is version 2 of Rocky. And so whichever version of Rocky you'd like to run, I'm going to show a test here with version 2. So I'm interested in the one that's marked with index 3. Index 3 is right here. You need that piece of data. You need this piece of data. You need the IP address. Those are the pieces we're going to need in order to do our IB write command test. And so with an IB write command test, there is a server side and there is a client side. And so on the server side, we're going to run this command, but I've got to update it, I think. Yes, I have to update it. So CUDA is referring to the version of the GPU that we have. Since we only have 1 GPU in here, it's CUDA 0. If we had 3 or 4 GPUs, you'd want to specify which one do you want to use, 0, 1, 2, 3, however many. But we're going to leave it at 0 because that's what we got when we ran the NVIDIA command up above. The source IP we know is the .2 address because this is what's in this pod. That's what we need to define here. Our device is already set to the proper device, but if it had come up MLX5_2, you'd want to change that here to 2. And then finally, the index value is the -X here, so we need to change that to 3. That's going to enumerate differently every time you run this pod. I've run this particular setup before, and sometimes the index is 5, sometimes it's 3. So again, using the show gids command will get that information for you. The rest of the switches on here, you can leave them at the default. I don't know off the top of my head what all those switches are for. That's what man pages are for. So if you're interested in knowing what those switches are, I would recommend look at the man pages for the IB write BW command. And I want to point out at the end of this command, notice I left it with use CUDA DMA buff. So if you remember, we did compile the GPU drivers with RDMA true, which means the NVIDIA peer mem module is loaded. But I'm still going to use it with DMA buff. If I take the DMA buff off, it will use the peer memory module. If the peer memory module hadn't been loaded and I took the CUDA DMA buff off, this test would fail. So again, there's different ways you can run this test. I'm just showing it with the DMA buff option. And so this is the server side. So if I hit enter, now it basically just says, hey, I'm waiting for some client to connect. And so with that, let's jump over to the other pod and let's gather some information ahead of time here. So first we wanted to get our device, our index, our IP address. And again, we're going to use Rocky version 2. I'm not interested in looking at 1. You might have a reason for it, but in most cases, people are doing version 2. And so now let's go ahead and craft our client command. It'll look very similar to the server command. In fact, almost identical. The only difference is is that after the use CUDA equals 0 is we've got a destination IP address. That destination IP address, the .2, is the pod running on worker node 29. And then notice we've defined our source as .3 because that's what our IP address is in this pod. Our device is the correct device. We've got to change the index value here to 3. And we're going to go ahead and we're going to hit enter. And this is where it actually runs a test. This test takes about 60 seconds to run. And we're really just interested in the BW average gigabits per second. And so that's going to take just a few moments here to run. Is there any outstanding questions out there, or are we just kind of waiting?
No, we're trucking along. Yeah.
Okay. And if we've got time, I'd like to show the InfiniBand one as well. So, but go ahead.
Yeah, let's do it. I was just going to ask what the BW is.
It's the writes bandwidth test is what it is.
Okay.
There's a write BW, there's a read BW, there's also a read latency and a write latency. To me, I feel like if the write bandwidth looks good, I feel comfortable with the rest of them. I don't necessarily am concerned about reads. I mean, if I'm getting really good writes, then I feel like my reads will be really good as well. Now, this is what I was waiting for, because people are going to look at that and they're going to be like, well, that doesn't seem very exciting. And it's not. This particular test harness is not really designed for the best optimal performance. And I'm going to show you guys a couple of different reasons why. But that 93 gigs per second is not very good because the connection between these two nodes is over a 400 gig link. And so this really doesn't show the value. But again, it's because of the way this test harness is set up. If I'm going to get this going. I'm going to take off the CUDA part and run this test again without the GPU, just so that you guys can see that this is a good link and I'm not just trying to, throw smoke in the air. And then I'm going to show you the reason why this isn't a good test harness to show the value here. But again, this is a 400 gig link. We only got 93 gigs per second. That doesn't look very good, right?
Right.
And so there's a reason for it. We just have to kind of wait for it. And I'll tell you. So keeping everybody in suspense. But this will show you that the actual link is a good 400 gig link when I take the GPU out of the picture. Now, what I will say is the values that are going to show up at the end of this test, I have seen those with partners when we've done testing with the partners. I think Cisco is a good example, but we were using H100, H200 type nodes. And so that's the big difference here. Remember, this is just a Dell R760 XA box with a couple of slots in it and stuff. So these aren't necessarily designed for the optimal performance that an H series or even an A100, any of the DGX line would provide. Oh, yeah. But I can show you that my link truly is a 400 gig link, and I almost get line speed just between the NICs when I'm doing an RDMA, IB write test. But again, that's without the GPU. Now, the reason we don't see so much of a value with the GPU being involved is because if I do a NVIDIA SMI command and I do topo, this is a good one to make your friend as well, and I run it, what you're seeing here is I've got one GPU and I've got a couple of NICs. One NIC is being the actual cluster network NIC in here, so that's of no value whatsoever. But you'll notice that where they cross, it just says node. So NIC 1's node. Anytime the GPU and the NIC cross, it's just node. Well, if we go down here to the legend, here's the reason why. My connection is transversing PCI as well as an interconnect between a PCI host bridge within a NUMA node. So think back to those actions I showed on. Remember how we were talking about directly PCI switch? Well, if my GPU is on one PCI switch, NIC card is another PCI switch, now my data has got to transfer across PCI switches, and that induces latency. And so systems that have either the sys or the node listed, they're not effectively going to be your performance systems. But if I had an H100 here to show you, and I did this topple output, what you would see is things like picks. And when you've got picks, that means that my GPU is sitting on the same internal PCI switch as the NIC card itself. And NVIDIA will refer to these as a rail. They're on the same rail together. And if that's the optimal you can get, if I've got a GPU on the same rail as the NIC, that's the best performance you can get. The only thing that'll help make it even more performant is if you're going to see this NV number. And that's where we've got all the GPUs NV linked together, because that creates a mesh of just the GPUs on the back end, so that you could potentially write across any of the NICs on the front end. So PICs is where you ideally want to be. As you go back, to PXB or PHB, and then you get to node and sys, that's where it starts to drop off, because you're dealing with multiple hops in the system. You're introducing latency because of situations where you're not in that optimal scenario. And that's the reason why we see the 93 gig here in this environment with converged Ethernet.
Gotcha.
So let's take a jump over now to these InfiniBand ones, because I want to show you that really quick. And so these definitely should be ready for us. And so now what we're going to do is, first I'm just going to do an IPA here, because I want to show you that our Net1 interface, which is our InfiniBand interface, and it even says it's an InfiniBand link. Notice it's got an IP address on it. And again, that's where that IB over IP comes into play, is that we can reference this interface via an IP address, but in the end of the day, the connection between this pod and the other pod on the other worker node is InfiniBand. And I can even ping that other pod here, but the actual data is going to be running over an InfiniBand link. You can see it's .5. Now, the other thing to point out here is, notice that this pod got a .4 address and the other one got a .5. Well, if you remember, I was using the same subnet for both my converged Ethernet and also my InfiniBand. And so Whereabouts is keeping track of that. And so Whereabouts is keeping track of that same subnet for both, which is the reason why I got a .5 and a .4 address on these InfiniBand pods. If I had to use different subnets, then I would have gotten a .2 and a .3 in my scenario. But since I left them both the same, so just pointing out that Whereabouts is keeping track of all of this, and that's the reason why it thinks that .2 and .3 were already used, because there's two other pods running with those IP addresses. But you can't ping them from here. That's the other interesting thing. I can't ping a .2 from here, even though it's in the same namespace. Oops, I can't use that command, can I? I can't ping them because they're running in a converged scenario, and this is an InfiniBand scenario. So there's no communication between those two when it comes to that. So anyways, let's go ahead and run our show GIDS command, which isn't necessarily as valuable here, but it's still important. And you'll notice here, we don't have multiple versions of Rocky, because this is an InfiniBand setup. So it's just, you get what you get there. So let's go ahead and plug in the server side here. Yeah, the show GID seems to be more important for the Rocky stuff, but you're still going to need it here just to make sure that the index is set properly and that the device is there. And so our IP address is .4. Our device is 5_0, so that stayed the same, and our index is already set to 0. So we're good to run this command. So I'm going to kick off the server side. Let's go over and do the client side. And again, this command should be the same. There wasn't much change here. And again, our destination is the .4, which is the other pod. So let's go ahead and run that. And again, this will take about 60 seconds. What you're going to see here is that the BW average here is actually faster than what we saw in the Rocky test. And I think I have an explanation for that, but I don't necessarily know it for certain. But I think I believe I know what the explanation is there.
So this is going to be similar to the first test that you ran, where it's running through the GPU, but this time just instead of it's going over the InfiniBand network, right?
Exactly. So yeah, we've
Okay.
included the GPU. It's going to be GPU NIC card out, going into the NIC card into the GPU. The only difference here is this was InfiniBand fabric versus the first one was that converged Ethernet fabric.
This is a great demo, by the way.
It's the first time I've done it like this.
No, I mean, it's for me, like I don't deal with this stuff at all. And to go into a deep dive like this, it's been enlightening. It's awesome.
So you'll see that the average here is like twice as much as we got on the converged Ethernet one. We're up to 181. And this is usually the standard number that we do see in this environment with these systems. And so the only explanation I can think of is the InfiniBand switch that this is plugged into really doesn't have a lot of hosts consuming on it. So like we may be the only ones that actually passed any traffic in the last hour doing this test. Whereas the converged Ethernet, that switch is a Spectrum switch from NVIDIA as well. It is got a lot of other different work streams and stuff going on it. So there might be additional traffic and overhead that's potentially reducing our ability to at least get to 181 gigs per second here. That's the only explanation I can think for this, because we're looking at the same boxes here. We're running the same commands. Basically, it's just InfiniBand over Ethernet. But you can see it's definitely much better here. And if we went ahead and did this test without the GPU, I'm guessing we would see that line rate again. And I actually didn't do this test before I'm showing it here live, so I'm not really sure what to expect here. But I'm assuming it's going to give us line rate. So again, to use these tools and to use this image, I do have a GitHub repo that's publicly available. It shows you how to build the image. It shows you how to run the image. It shows you examples of what you can do with the image. And what I'm not going to show here today is a nickel test, but there is an example of a nickel test in there. There's also an example of showing how to make firmware changes. Like, again, do I want to enable SROV on the NIC card? Do I want to set the number of VFs? So there's examples in that GitHub repo of what you can do with this particular image. But again, since it's all basically, open source, anybody could take that image and fashion it to their own needs. If they wanted to add their own tools that are related to their own organization, they could easily do that and build a custom image. But again, I was just trying to provide a common ground that we can all work from, so that when you come to me and ask for help, using an image, I know what we can do on it and how we can get information, as opposed to an image that doesn't necessarily contain all the bells and the whistles.
Well, and that's the whole point of containers, right? Is to be able to have that common platform that you can build and reuse. So, yeah.
Exactly. So you can see we got line rate here again without the GPUs. And again, we understand that the reason why we get line rate without the GPUs versus with the GPUs is because we're not in an optimal configuration rail setup here on these Dell boxes like we would be if we were using, heck, even if we were using a Dell, what is it, the 8960s or something like that? They're kind of like the H100, H200 equivalents that Dell ships. Those would have the optimizations built into the hardware where you've got GPU and the NIC card on the same rail, so you could get the benefits.
Gotcha.
So that was kind of all I had. I mean, at this point, we validated the infrastructure and we've done some tests. I feel confident now that we could literally take OpenShift AI and we could deploy it on here and it would run effectively, and we could run an LLMD that needs to, work across multiple GPUs. Unfortunately, that's not part of my demonstration today, but at least it gives you an idea that, hey, you're ready to go to deploy your workloads and feel confident your infrastructure is set up properly.
Yeah, this was, again, I think this was an excellent demo. Like, I think going through and showing, like the different configurations and how, like, what happens if you don't need it or if you don't apply it, and showing the output of like, hey, this is with the GPU, without the GPU. I think it's, very, very good. If you ever want to come back and do a demo with OpenShift AI and some stuff on top, let me know, because I think that'd be cool too. Like, if you want to build on it.
Well, we can always come back and talk about the things that are in the pipeline, which is DPF, which allows you to provision DPUs in an OpenShift cluster. So that's right now, it's like in a tech preview scenario. And so they're trying to get it to GA. Then the next thing is going to be Spectrum X, and not Spectrum X just from a switch perspective, but a full software stack that NVIDIA is promoting. And so what does that mean? Well, you're going to have Spectrum switches for your east-west traffic in a mesh. You're going to have spine leaf setup. And then what you're going to end up with on the OpenShift host is you're going to have some software that gets configured. And some of that's going to include the NIC configurator operator, which will be part of the network operator, that will actually deploy the appropriate firmware for the Spectrum X software stack. And then there'll be some configuration that occurs from the SROV level, which will configure some flows and some bridges. But the idea here is that it's going to give you the most optimal performance from not only the host perspective, but on up into the switches. And so that's something that we're currently working on. And eventually that too will be something that people will see in a GA scenario.
Nice. Awesome. Well, dude, thank you for coming on. I really appreciate it. If you're watching the stream after the fact and you have questions, feel free to email myself. I'm Jonny@redhat.com. Ben, I don't know if you want to give out your email, but if you have questions for Ben, feel free to send them to myself and Sully, SULLY @redhat.com, and we'll get them to Ben.
People can send it to me. It's just B Schmaus. Make sure you spell it right. And I see in chat they've got the Schmaus Tech in there. So B and then Schmaus @redhat.com will get you to me.
Awesome. Yeah. So if you have questions, feel free to ask us. We love to answer them. Ben, thank you very much for coming on. I really appreciate it. I really think that this demo was awesome, and appreciate you taking the time to put it together. It was really well done.
Well, thanks for having me. I really enjoyed being on here.
Awesome. Anytime. All right, cool. So next week, again, we have the Red Hat TAS Trusted Artifact Signer, and then I think the week after it is it's going to be confidential containers, and then there's so much going on I can't remember, but those are the two big ones that are coming up. So looking forward to it. Ben, again, appreciate you coming out. Would love to see the next stage of this and build up on top of it. And thanks again. Have a good one.
Take care, everybody.